This is the fossilized skeleton of an ichthyosaur. Its anatomy is highly specialized. A streamlined, fusiform shape evolved for efficient movement through a dense fluid. A modern dolphin mid-leap exhibits the same hydrodynamic profile. The two animals are separated by millions of years, yet their silhouettes are nearly indistinguishable. These species share no recent common ancestor. Their genomes are distinct, yet their macroscopic anatomical form is identical. We see this across the tree of life. The eye of an octopus features a lens, an iris, and a retina, a camera-type structure that mirrors the vertebrate eye, despite a completely separate evolutionary origin. This consistency challenges the assumption that DNA acts as a one-to-one blueprint for biological form. If development were a hard-coded set of instructions, unlinked genomes would not repeatedly arrive at the same complex mechanical solutions. Regeneration experiments provide further evidence. The planarian flatworm is defined by its distinct eye spots and specific boundary geometry. When a planarian is cut into pieces, each fragment restructures its remaining cells to form a complete, scaled-down body plan. This requires a coordination that a rigid linear blueprint cannot provide. This behaves like a topological flow field adjusting to a new container. When the boundary changes, internal currents reshape to find a new equilibrium. Observer resonance theory proposes that while the genome provides local material constraints, a thermodynamic field computes the body plan. A biological organism is a bounded thermodynamic resonant container, and its form is a solution to the laws of physics. Any bounded container restricts the wave states that can exist inside its volume. Chaotic external waves entering a boundary cancel each other out through interference. Only stable standing waves, the eigenmodes, remain. This acoustic equivalent shows how boundary shape dictates internal pattern. The vibration forces physical matter to settle in specific regions. The geometry of the plate determines the pattern, rather than the properties of the sand itself. The observer boundary reconstruction principle applies this physics to living systems. An organism's internal function is determined by the eigenmode spectrum generated by its outer geometry. Because the geometric interface writes the physics of the interior, a biological body cannot remain homogeneous. A biological boundary is multipolar. It features specialized interface points, intake poles for food and oxygen, and dissipation sinks like skin or lungs. These interfaces interact with different entropy gradients, ranging from chemical and thermal to mechanical and phase. Incoming flux must be transported across the interior, moving from the source interfaces to the sink interfaces. Where these flow pathways intersect, internal eigenmodes stabilize. They condense into persistent hubs to process the flux. These stabilized nodes are what we identify as organs. The heart, a mechanical pressure mediator. The gut, a chemical decomposition mediator. Each is a persistent sub-observer, converting specific entropy into internal coherence. These structures are thermodynamic necessities. An organism develops internal mediators to process the flux, dictated by its specific boundary. Morphogenesis is fundamentally a mathematical variational problem. This is the body equation, and demonstrates that anatomy solves for the minimum possible action. A star is the optimal anatomy, and S body represents the total entropy produced by the system. Possible anatomical arrangements form a topological landscape. Most configurations sit on unstable peaks, where entropy production leads to decay. An arbitrary arrangement of organs results in flow failure. The system cannot maintain its coherence. Viable body plans are sparse attractors. They are the rare basins where entropy production is minimized. The genome dictates the shape of the landscape, but the thermodynamic field dictates the descent into the anatomical basin. This raises the question of what distinguishes a living body from other ordered structures like crystals or hurricanes. True life is defined by two parameters: recursion depth and generative emission. Recursion depth means condensations within condensations, the nested organization of organelles, cells, and organs. Generative emission is the ability to use internal coherence to construct and emit new boundaries into the environment. Life begins at the threshold where a thermodynamic system achieves sufficient recursion to trigger generative emission. In this framework, life is recursive super-Q resonance reaching a critical structural depth. This explains why distinct genomes consistently produce the same biological hardware. When two different lineages face the same environmental constraints, they enter the same thermodynamic funnel. Identical boundary conditions force both systems toward the same anatomical solution. The camera-type eye is the lowest entropy attractor for visual data in a multipolar optical environment. The fusiform body is the optimal solution for moving mass through water. Evolution is simply a thermodynamic optimization process. The physical field forces the anatomy into a specific basin, regardless of the genome's heritage. Under the observer resonance framework, the biological organism is a standing network of physical forces. Form is dictated by boundary. Function is dictated by eigenmode. The principles are precise. An organ is stabilized function, and anatomy is the physical memory of entropy resolution within a bounded space. Ultimately, life is just geometry solving entropy.